So right now we're going to be doing questions based on latent heat, specific latent heat. So let's get started. So these are the first 6 questions, and then I'll put out the next 6 questions. I got these questions from a textbook by Onash, so therefore I will not be monetizing this video. I want you to learn, so without any interruptions. So here goes. How much heat is needed to change 20 grams of ice at 0 degrees Celsius to steam at 100 degrees Celsius? So when it comes to these questions, when you're moving from solid to liquid to a gas, you always draw out. When it comes to latent heat, remember latent heat means that there is no change, no temperature change when there are phase changes. Okay, so you always start from where the question wants to start from. So it says, how much heat is needed to change 20 grams of ice? So let's start drawing 20 grams of ice. And if you're not someone that likes to draw, you could always write it in words, but I like to draw because you could see it nicely. 20 grams of ice at 0 degrees Celsius. And so to go to steam, it has to go through a bunch of changes first. So it must change phase from ice to water. And remember, during phase changes, there is no temperature change. So from ice to water, from ice to water, or from ice to liquid water, we have no change in temperature. So that's latent heat right there. I'm going to label this arrow A. And then now we're gonna heat up that water to all the way 100 degrees Celsius. That's the same 20 grams. So we're gonna act as if this is being done in a closed system, right? And then it says, if you look at it, it says from ice to steam. So now we're gonna keep boiling this water until it becomes steam, right? This is the same 20 grams of water, now it's steam. And remember, you're going from liquid to a gas. So that's another phase change right here. So here you have to acknowledge that at this phase change, there'll be no temperature change at all. And that is why you're going to have latent heat happening in this section. So we're going to label all the arrows, A, B, and C. Now, whenever you're going from a solid to a liquid, or from liquid to a solid, you're going to use a specific latent heat of fusion, which is 340. This is ice. So remember, ice is the one that goes from solid to liquid, and then you have the liquid going to solid. So this one is a latent heat of fusion, right? So this is LF right here. And then if you're going from water to a gas, or from gas back to water, or to liquid, from liquid to gas, or from gas to liquid, you use this one. And you think of it in terms of water, because usually you're going to hear a lot of questions use water. And so this will be our latent heat of vaporization. And note the units. These units are in joules per grams, but the SI unit is joules per kilograms. But since we're using joules per grams, you're going to notice a lot of our masses are going to be in grams. So because there is no change in temperature, this involves latent heat. Okay, and since we're going from solid to liquid, we're going to use 340. And we're going to use latent heat of fusion, solid to liquid. So we're using latent heat. Okay, so mass times latent heat of fusion. Here in this case we have a change in temperature, so definitely we're going to be using heat given off, right? So here, heat taken in, So this is our heat taken in, so that we could start breaking bonds. So because there's a change in temperature, we have to use MCAT. So mass times specific heat capacity times delta T. And then now we have no change in temperature, so here, so we're going to use mass times latent heat of vaporization, because we're going from a liquid to a gas. Now please bear in mind that we have a bunch of equations that we can use. Remember, we can use EH equal to MCAT. We can use EH equal to MLF, or EH equal to MLV, or EH equal to power times time, or EH equals to mv squared over 2, and this is kinetic energy, or EH equal to mgh, and this is potential energy. So remember, I told you all of these are related to heat given off or taken in at some time, because these are all equations for energy. And energy, anything that involves energy, will give off heat, you know. So since we have all of this, it says how much heat. So we have to solve A, B, and C and find the total. Now for A, we know the mass. We have the MLV, so let me write it here, MLF, sorry. And the mass of the ice is 20 grams, which is fine because the units here are in grams. And the latent heat of fusion for ice is 340. Okay? 340 joules per gram. Now for B, we're using MCAT, and the mass is 20 grams. The specific heat capacity of water is 4.2 joules per gram degree Celsius, and the temperature change is 100 minus 0. So you always want the cooler temperature from the warmer temperature, so that we avoid negatives. So we're here, okay? And then for C, we're using MLV. And here we're going to use 20 grams times the latent heat of vaporization of water. So this one will be 2300 joules per gram. Okay? And so now we could work them out. And what would you get? You could work along with me as well. The first one is 6800 joules. The second one is 8400 joules. And the third one is 46,000 joules. If you add those up now, 8400, you should get, so A plus B plus C. You don't have to put back the numbers if you already stated what your A is equal to. It will give you 61,200 joules. So that's how much heat is needed. So that's how much heat is needed to change ice into steam. 20 grams of ice into steam, right? Great. Okay, so in the meantime, what I would like you to do is make sure you write down these equations, so you could determine whether you're going to be using the first one, the second one, the third one, the fourth one, the fifth, or the sixth. equation. And what I could possibly do is probably just put it there above all of my working. So I'm gonna write them down. Equal to MCAT, EH equal to MLF. Okay, so make sure you write them down just in case I change my mind. Okay, so here we have another one. I'm gonna put back here. I'm gonna write in yellow now, or green. Let's write green. So I'm gonna put back here that this is going from gas to liquid, or from liquid to gas, and this one will be going from solid to liquid, or from liquid to solid. Okay. So this is our second question, and again, remember our equations that we can possibly use. EH equal to MCAT, and I think I'm gonna write this every time I do the question, so that eventually when you hear me talk about it all the time, you're gonna hear me talking in your sleep, right? I hope that's a good thing. So EH equal MLF, and guess what? The next one will be EH equal MLV. And then the next one will be EH equal to PT. Then we have EH equal to kinetic energy, which is mv squared over 2. And then we have EH equals to mgh. How awesome is that? Now, an aluminum can of mass 100 grams contains 200 grams of water. Both initially at 15 degrees Celsius are placed in a refrigerator at negative 5 degrees Celsius. Calculate the quantity of heat that has to be removed from the water and the can for their temperatures to fall to negative 5 degrees Celsius. So we have two things to look at. We have to look at the can, and we have to look at the water. And we always look at what they give us. They gave us aluminum, and they gave us water, so we have to look at these two. So first we could do the can, because remember, aluminum is not going to go through any phase changes, right? It's not going to change from solid to liquid. It's going to stay solid whether or not it's hot or cold, right? So looking at aluminum, we're going to list all the things we have for aluminum. So we have the mass. So the aluminum can has a mass of 100 grams. We are given the specific heat capacity, because what we see is that it goes through a temperature change. Well, let's see. So let's list what we have. So C is 0.90 joules, grams, degrees Celsius. And then we have the initial temperature, which is 15 degrees Celsius. And the final temperature, the equilibrium, will be met at negative 5 degrees Celsius, right? And so delta T would therefore be, we're going to subtract from the warmer temperature. So when we subtract from the warmer temperature, we're going to end up adding, because a minus and a minus will give you a positive. So we'll end up with 15 plus 5. All of these have the same units, and we're going to get a whopping 20 degrees. So if we work out the heat removed from the can, EH aluminum, we would see that we have 100 grams of aluminum times, we're using MCAT, by the way. So let's go back to that. So let's do that. So since we have MC and delta T, we could use MCAT, right? So we're going to use the MCAT because there's a temperature change, right? So we have solid aluminum, 10 grams of it, going from 15 degrees Celsius to solid aluminum again, 10 grams of it, aluminum, going to -5 degrees Celsius, right? So there is a temperature change. And remember, once I have temperature change, we use the MCAT formula. Okay? So because of that, we just we just substitute. So we have 10 grams times 0.90 joules per gram degree Celsius times 20 degrees Celsius. We cancel out our Celsius and our gram, and we end up with, hope you're working these along with me. It would help, because just looking is not going to concrete this. So let's go again. So we have, oh, it's 100 grams. See, 100 grams, my bad. So it's 100 grams, right? So 100 times 0.9 times 20 will give us 1800 joules. So that's one. So now we're gonna look at water. So it says that you have 200 grams of water and it's at 15 degrees. So we know that it would be liquid at that point. Remember, water freezes at 0, pure water. So we know at 15 degrees, 200 grams of water would be a liquid. So we put 15 degrees right here. And then we put it in the refrigerator that is at -5 degrees. So we have to start the freezing process. So water will begin to freeze or become solid at 0 degrees Celsius. So therefore, we're going backwards. So you're going to have a phase change from water. So therefore, you're going to have water changing from 15 degrees to 0 degrees. Okay? So you have that 0 degrees right there before it even changes into water, because remember, you have to go through that phase change where there is no change in temperature. Okay, so that is what keeps us sane in this whole process. And then from there, that ice will further cool down to 15 degrees Celsius. So, sorry, to -5 degrees Celsius. Okay, so here we have our drawing. Just remember, whenever you're doing phase changes, you can't just go from water at 15 degrees to ice in a solid form at 0 degrees. You have to pass through some sort of phase change. So it will go to the ice at the icy water at 0 degrees Celsius, and then that icy water would then go through latent heat. It will lose its you'll see bonds broken, but there'll be no change in temperature then. So this is where the latent heat comes in, because remember, during latent heat, it appears that heat is hidden, and it appears that no heat is given off. It's just bonds being broken. So in between this time, there's no change in temperature. Okay? And so I'm going to label these arrows A, B, and C. So we have 3 workings to do. So between this point, the 15 degrees and the 0 degrees, there is a temperature change. So therefore, we'll be using the MCAT scenario or equation. Whenever there is no change in temperature, you're definitely going to use a latent heat of a specific latent heat equation. So it's either going to be fusion or vaporization. So because we're going from liquid to solid here, we're going to use latent heat of fusion. So this is fusion right here, and this is vaporization right here. So we're going to do MLF. And then now we have a temperature change of 0 to -5. And since that's a temperature change, you're gonna just use MCAT. Okay, so I think the easiest thing to determine is the temperature changes, because it's obvious, right? It's just for you to remember whether to use latent heat of fusion or vaporization. You just have to put it in your head that once you're going from solid to liquid or from liquid to solid, you're definitely using latent heat of fusion. Okay? And once it's from ice to liquid or from liquid to ice, you're going to use 340 once you're dealing with water. Okay? So let's start with A. And for A, we're going to have MCAT. So that's EH. So maybe I should put the EH equal to. So you get your full points. So we don't want to show off or anything. We just want to make sure that the examiner knows that we know or understands that we know what we are doing. So we have EH of the water equal to MCAT. And so we're going to say 200 grams times the specific heat capacity of water, because we're dealing with water here, which is 4.2 joules per gram degrees Celsius. And then we're going to have the temperature change, which is 50 minus 0. Remember, it's the hotter or warmer temperature minus the cooler temperature. And I'm going to put equal sign here, but I'm pretty sure I ran out of space. So, oh, look like I have a little space. Okay, so I'm going to put an equal sign right here. And then we have B. That's the B. And so B will be EH of the water and MLF. So LF is one thing. And again, we have the mass, 200 grams. And the LF would be, the latent heat of fusion would be 340, because we're dealing with ice, water to ice. So that will be joules per gram. And then we're going to do C now, where we have EH of the water again. And we have MCAT. And in this case, we're using the mass of water. But this time we're using the specific heat capacity of ice, because as you can see, we're dealing with ice here. So look for the specific heat capacity of ice, and we see it as 2.0 joules per gram degree Celsius. And then of course the temperature change would be the warmer temperature minus the cooler temperature. And if you notice, you're going to end up with a positive number. This one for sure. I don't know if I'm going to be able to stay on this line. But let's work this out now. So it's 200 times 4.2 times 15. And that gives us 12,600 joules. Because the degrees Celsius will cancel out and the grams will cancel out. So let me just cancel them out. And then we'll say 200 times 340. And we have 68,000 joules. So the grams cancel out here. And then we have 200 times 2.0 times 5. And we end up with 2200. Joules. Alright, so I ran out of space. And if I add all of these up now, so A plus B plus C plus EHAL, so we're going to add, let me do now, total EH will be equal to 12,600 joules plus 68,000 joules plus 2,200 joules plus 1800 joules, and that should give us 84,600 joules. That's a lot of energy. That is a lot of energy. I hope everybody got that. Let's see right here. Just making sure. $200 times 2 times 5. What did I do? Oh, I made a mistake. So it's 200 times 2 times 5. That would give us 2,000. My bad. Sometimes you make these mistakes. Alright, so I'm going to change this 2,000 to 2,000 right here. Subtract that. So it's 84,400 joules. So I hope we all got this. So yes, I made a mistake. I'm very sorry. So recap, remember that the aluminum will not change phases because it will stay a solid whether it's at 15 degrees or -5 degrees, and hence you will just have a temperature change happening here. So that's a one-time calculation. However, water will go through a bunch of changes of states, and so you will have different calculations for each transition. And you're also going to have a bunch of changes in temperature. So you're going to have temperature changes as well as state changes. Hence you have multiple calculations to perform. Also, remember, if something is going through a phase change, it will first move from whatever it is at to its specific freezing point in that state that it was originally at, and then when it is done doing that, it will change phases at the same temperature. Okay, you'll get the hang of it when we move on. So this is question 2, and this is the answer right here, 84,400 joules. Okay, so here's question 3, and now I'm gonna use let's use blue, bright blue. All right, and again I'm gonna write the equations right up here. EH equal to MCAT, EH equal to MLF, EH equal to MLV, EH equal to PT, EH equals to mv squared over 2, and then EH is equal to mgh. Okay. So remember that this one, the specific latent heat, this one goes from gas to liquid or from liquid to a gas, and this one will go from solid to a liquid or from liquid to a solid. Okay, and so this one corresponds with latent heat of fusion, and this one is latent heat of vaporization. So the L and the V and the L and the F are two different entities, but we look at them as one entity by itself, if you get what I'm saying. Well, you see. Alright, so we have two parts, 3A and 3B. How much heat will change 10 grams of ice at 0 degrees Celsius to water at 0 degrees Celsius. So there is no temperature change in this question at all. So let's start one. I'm going to pathways right here, and this will be question A. If we draw this out, we have the ice, we have the 10 grams, and we have degrees of 0 and there, and then it's being transformed, it's changing state into liquid, and we have 10 grams of that liquid at 0 degrees Celsius, right? So how much heat will change this? So since this is basically no temperature change, we're definitely going to be using MLF. So we're going from solid to liquid, right? So because of that, the calculation shouldn't take long, and so we're going to say EH, right? So EH of the ice will be equal to 10 grams of it times 340 joules per gram, and that will give us 3,400 joules. So that's how much energy will be needed to break the ice down, right? Now let's do B. B, it says what quantity of heat must be removed from 20 grams of water. So we're going in the reverse now. 20 grams of water to change it back to ice. So this time, in this case, we're using 10 grams. We want to know how much heat we must put into the ice to convert it to water, right? And now in this case, we want to know how much heat must be removed from the water, 20 grams, double the amount, to change it back to ice. So we're going from water here, and we have 20 grams, okay? And it's at 0 degrees. There is no temperature change, so we're going directly into cooling, or if you want to call it freezing. And we want to form 20 grams of ice. And there is no temperature change, so therefore there is no temperature change. We don't use MCAT. And so this is just one arrow. And since we're going from liquid to a solid, we're going to use MLF, fusion, right? So EH of the water, that is twice the amount in this case now. EH of water will be equal to, I didn't put the M times LF for those of you who need to see it. So M times LF. And so the mass of the water is 20 grams. And the latent heat of fusion, so remember I told you if you're going from liquid to solid, will be 340 joules per gram. Cancel that out, and it's definitely going to be twice this. So it's going to be 6,800 joules. So if it's twice the amount of mass, you're going to need twice the amount of heat, right? So that's just all it's trying to tell you, okay? So I hope you were able to understand this question.